Thank you very much, Amy, for the opportunity to speak here. It's been great to actually work with you previously, and it's great to actually have finally one of these meetings here in Melbourne. So this is great to be able to talk to you about some of the work that we're doing at CSIRO, but more also to talk about the value chain for natural graphite and where natural graphite plays specifically into the battery value chain. This is work that we do here in our Clayton laboratories, as well as with our colleagues in our Perth Waterford facility, where we are able to do pilot scale development of graphite processing. Feel free to stop me if you have any questions during this presentation. It's probably a little more on the technical side, but hopefully I can get it to a level where you can all appreciate some of the technology here. So at CSIRO, we do battery research across the full value chain. We're the only organisation in Australia that can do this. So we can go from discovery of mineral ore bodies, we can look into the processing of those ore bodies, and you'll see there on the top left-hand corner, we're looking into lithium, cobalt, nickel, manganese, and vanadium as areas of interest, because these are all key mineral elements that go into today's large-scale energy storage technologies, so both either lithium or redox flow technologies. And in fact, some of these minerals will also be applied to emerging technologies such as sodium-ion, which you might have all heard of recent times, which is considered to be a cheaper version of lithium, but has a much lower energy density. We then move from that processing work to battery materials, so those upscaled value-added materials, and we're looking at those final stage products such as lithium carbonate, lithium hydroxide, but then some of the advanced cathode materials that are used today, such as the NCA that's developed by Panasonic and used in Teslas, NMC materials that are used in other high-energy batteries in automotive, and of course lithium-ion phosphate. One of the key technologies there I'll talk in more detail to you shortly is also around graphite as well. We also look at electrolytes, and we also have an interest in next generation lithium metal technologies through our Lithium technology. We can pilot these materials into batteries in our facility here in Clayton. We can turn these into anode and cathode materials and then make either small-scale pouch cells for validation, which would be a step before you'd go into pilot-scale manufacture. We're interested in next-generation technologies such as lithium-sulfur, lithium-air, but we also look at the packaging of battery technologies, and we've worked, as an example of this, we've worked with Energy Renaissance, Australian battery manufacturer in Tomago, New South Wales, who has Australia's first gigafactory, to actually help develop their technologies that they now manufacture and sell. Our deployment work is through our energy business unit. We're very interested in how energy is used and deployed, and then we're also interested in second life and finally the recycling of these materials. Recycling will be critical in order to be able to maintain the volumes of material that will be needed now and into the future for energy storage. So graphite, the what and the how. Why are we interested in graphite? Well, graphite comes from carbon. It's a single layer material, and those interstitial layers that you see there on the image on the right-hand side underneath that carbon block is where lithium is stored. It's that interlayer spacing is which is the really criticality that's required. The more graphitic a material is, the more lithium that we can store in there. Amorphous carbon is no good here. It's nice for electrical conductivity, but it doesn't actually store any energy. So from that, we can then, you get obviously different allotropes of carbon. So of course, diamonds are a girl's best friend, but they're not very good for storing lithium. And then of course, we can go to get that type of stuff is obviously mining. And Australia has actually quite some substantial reserves now, and more being discovered of natural graphite. And this is particularly found in Queensland, southwest Western Australia, and also down on the Eyre Peninsula in South Australia, where there are a number of different graphite miners active there. To get the difference though between natural graphite and synthetic graphite is actually quite substantial. Generally, synthetic graphite starts from petroleum coke material, that then has to be heated at extraordinarily high temperatures to graphitize it over a period of time, so it's extraordinarily energy intensive. And then from there you then have to then process that further, and you'll see there that some of the temperatures that are being required there, down at greater than 2,500 degrees Celsius, what makes this extremely problematic as a material manufacturer. For most part, this work is done in China, as energy is substantially cheaper there, and that makes it more affordable to do this. So this is when we think about graphite in Australia, and in terms of natural graphite, here's the type of things that we're looking for. As you go from amorphous carbon at lower temperatures, this is what has very good ionic conductivity and electrical conductivity, and this is what's used to coat graphite. And through to, as you go higher and higher in temperature, we see more of this lattice ordering until we get to the graphitic material that we use inside a battery. And that graphitic ordered material is what's needed for battery materials. In terms of uses, there are 6. You can see here in this plot that up until about 2019, graphite as a use material in batteries was actually considerably lower. And in fact, the single biggest dominant use of graphite is in electrode materials, and that's for aluminium electrowinning. You need an anode for that material, and graphite's particularly good for that. You also see that refractories also make up a significant amount of material as well, and also as a lubricant is another area of interest. But as you can see, the blue bar in the bottom right of that image shows the continuous growth in the demand for graphite. Interestingly, now there's also a new emergent area for the use of graphite, and that's in thermal heat storage. So for particularly lower grades of graphite, where you don't need that ordered and highly graphitized type material, thermal storage is a really interesting opportunity, particularly for low heat applications in manufacturing production processes. So one of those areas of interest is pencils. Graphite is what holds up our pencil industry and is used for the lower grade stuff. You can also see that there's some of the use in brake pads is another area of interest. Refractories, and then further again up until we get into electrode materials, as I mentioned, and of course batteries. So where do we find graphite today? So graphite has quite substantial numbers of places for mining. So China has natural graphite, as does Russia. But interestingly, Africa has quite substantial amounts of it through Madagascar, Tanzania, and Mozambique. And for local people here, CSIRO Resources, I think, mines out of Mozambique and then transfers its material to Louisiana, to their facility in Vidalia, where they do the processing of that material to battery anodes. And they have a proposed offtake agreement with Tesla, which will be using that material. There are other Australian miners active in Africa, such as Ecograph and International Graphite. They are actually planning to do their actual processing in Kawana in Perth to turn their graphite into value-added materials. The other place where there are substantial amounts of graphite is also in Scandinavia. Particularly Australian miner Talga has quite substantial resources there, and they've actually built out a full anode value chain there, where they're now looking at how they can actually go from mining to actual anode material, and they have produced a proprietary material called Talnode, which uses their graphite together with a silicon additive, and they're aiming to supply this to Freya Battery Company into the future. Some of the more prospective areas of graphite, as according to the USGS, is Turkey has, by all accounts, quite significant reserves, but they're yet to be tapped. And of course there's also some interest also in South America. But Australia is obviously where our interests lie here. So how does a battery work, and why are we interested in graphite? So in 1974 was the invention of what we know today as the lithium-ion battery through the work of Stan Whittingham and John Goodenough, and they discovered the positive electrode intercalation processes that we know and understand today. So those particular materials were In the first instance of Stan's work, titanium disulfide as a lithium storage mechanism, and John Goodenough, lithium cobalt oxide. And for everyone in the room, you're probably using a lithium cobalt oxide battery today, because that's the basis of all our potable electronics. What makes a full battery, though, is the anode, and all lithium-ion batteries use graphite as their anode. That's the first thing to remember. There is a dominant material in a battery, and that's the anode material. And as you can see here in the image, in charging, we're moving lithium ions from the cathode to the anode, where we store the lithium in the interstitial layers between the graphite sheets. And then under discharge, those lithium ions leave the anode and moved to the cathode. So the real reason we love graphite is that it has what we call a high specific capacity, i.e. the amount of energy it can store per unit mass. And this is 365 milliamp hours per gram. So 365 milliamp hours of capacity per gram of material. This is in excess of most other commercial materials. The only two materials that compete with this are silicon and lithium metal. And silicon is an emergent material in the marketplace, and this is because it has at least a factor of 10 higher storage capacity than graphite, but it has considerable challenges in terms of use. The other alternative is lithium metal, and that was where the initial lithium battery started, but there are substantial technical challenges in being able to plate and strip lithium in a reproducible manner for hundreds, even up to thousands of cycles. But also there's a supply chain challenge as well, is that there's not enough lithium metal available to actually supply the battery industry, and so there's a real need there to develop new technical solutions to actually break that bottleneck. So for this reason, graphite is the dominant anode material used in today's batteries. Additionally, you're now starting to see companies adding small amounts of silicon to these anodes in order to further boost the energy density of batteries, and most commercial cells now have between 4 and 7% silicon additive to increase the specific energy of that negative electrode. So as I mentioned, there's the graphite, and this is the reaction chemistry that we use. So for every 6 carbon atoms, we have 1 lithium. This is what we actually see inside a cell. For those of you who are really interested in this, you start with a very black material, carbon, at the start of lithiation. As we go through the number of different lithiation steps in that anode, you'll actually see the color of the material change, such that when you get to the fully lithiated compound, the LiC6, when we actually take the anode out of a cell, we see it has this very beautiful gold color, which is related to the lithium that's inside the cell. If you go into what we call an overcharge regime, i.e. we put the battery into an abuse condition, the actual electrode actually looks silver, and that's because you've actually got lithium plated to the surface of that material. So these charge-discharge steps, these colors also correspond to steps in the discharge profile or the charging profile of graphite that we as researchers can see and track and follow as to the state of charge of these electrodes. But more importantly, battery management systems can use those to track the state of health and the state of charge of batteries. So, as I mentioned earlier, graphite may be found around the world, but the dominant player in this field, and this is from 2020, this may have changed a little bit, but I wouldn't suggest too much, but China is the dominant player here in graphite. So you can see here they've got 79% of this market. The others are all small, and even we don't even rate in 2020 on that plot, as we still don't actually produce graphite material for actual battery production. So there's still quite considerable opportunity here for Australia, and particularly since there's been a very large reworking of the battery value chain as we know it. There's also different types of graphite. So vein graphite is a particularly interesting graphite that's potentially found in Sri Lanka. It's probably the most purest form of graphite. It's the easiest to use. It doesn't require as much processing to access, so it's a particularly useful type of material to get, and Sri Lanka produces quite substantial amounts of this material. Amorphous graphite is obviously the more common form of graphite that we find, and is used as a conductive additive inside batteries, and that can be made by a number of different methods. And the one that we're particularly interested in is flake graphite, and this comes from a range of different natural graphite sources. So one of the interesting things about this field is that depending on your mine, you'll have different types of graphite. So a mine site in Queensland and a mine site in Western Australia will not have the same grade of graphite, will not have the same flake size, will not have the same impurity matrix. Similarly, if I get a graphite flake from Mozambique or Tanzania, yet again, it'll have very different geological properties, and so we will need to understand those properties in order to be able to successfully recover that graphite from the source. And depending on the size of the flake of graphite, we may need to do additional processing before we actually try and turn this material into a battery anode. So the natural battery graphite anode chain is quite a long one. It obviously starts at discovery, but we'll ignore that for the moment, but we'll think about first mining. And the first thing that we do once we mine that graphite is we need to concentrate it. We need to get rid of the majority of the impurity matrix for when the graphite sits in. So depending on the grade of graphite, that can run from 3% graphite in some Chinese mines, also in some Australian mines, all the way up to 25, even 30% graphite. Obviously, the higher graphite content, the better value you're going to get from your mine side. So concentration occurs via crushing and flotation, which I'll go through shortly. Then we go into a process called spheronization, which is where we make small potato-shaped materials. Final stage purification, and you'll see there we're trying to get beyond 99.95% graphite. Why? Because lithium reacts with everything. You want the purest form of material you can to get the highest rechargeability in your device and the longest life. Carbon coating, that's very much a secret sauce of most battery OEMs. And then finally, turning it into a battery anode. And then those materials go into those cells that you see there on the top right-hand corner. So mining and concentration, what does this look like? So this is just a plot that I've taken from the Battery Minerals website. Please don't take that as any form of recommendation of their products, but this is just to illustrate the process. So again, depending on the grade of material, you may need to have numbers of different milling and flotation and screening processes. The lower the grade, the more crushing, the more flotation, the more screening. The higher the grade, the less of it. So that has an energy penalty, so one needs to be mindful of that when going through those type of processes. But you can see here the screening into drying into filtration, followed by a further flotation and potentially more regrinding depending on how fine the flake is. The finer the flake, the harder it will be to recover. So you may need to do further regrinding and flotation as needed. Finally, you get into bagging, trucking, and then that can go either to export or, as what's seeming to happen quite a lot nowadays, companies are now setting up their graphite processing facility right next to the battery manufacturing plant in order to minimize their environmental footprint. Once we've done that, and you've got your 89 to 95% total graphite flake, you'll want to turn that into these little potato shapes that you see here down on the bottom left. Why do we want to use little potato shapes? Well, they actually pack better in a cell. So when we think about energy density in the battery, we want to think about both gravimetric and volumetric energy density. So packing density, tap density, is of really critical importance in that regard. So making potato shapes is far more efficient than just using the simple flake graphite. Further, graphite reacts as well with the electrolyte. And so we end up with those hard edges on the graphite flakes. We get what we form called a solid electrolyte interface. And this material is the decomposition product of the electrolyte on that flake. And you want to minimize the amount of those decomposition products, because those decomposition products actually mean the battery is less efficient, will have shorter cycle life, and won't work as effectively. So for that reason, we spheronize to get rid of as much of those hard edges and the like to actually make that process as efficient as possible. So there are a number of different ways to do this. We at CSIRO, we use a NARA hybridizer, and what this does is we have a feed on the top of that instrument there where we can feed the powder in, and through a rotationary process this balls up the little flakes into the spheroids that you see on the left hand side. The NARA hybridizer is not a cheap piece of equipment, but it's far more efficient than, say, a spheronizing train that you would buy from China, which is cheap and cheerful, but does not have the high yields that you would potentially like to have. And so what you end up with, if we cross-section it, is this. You can see here all the flake particles are all being rolled in till you get this round ball. So that's just a whole bunch of graphite flakes packed in together, and that's where all the lithium is stored inside the cell. And so one of the things that we're trying to avoid here is also damaging the flake. So the more you process this material, sometimes the more you can make it amorphous. And when it becomes amorphous, then you don't have storage capacity, but it will be electrically conductive. So being able to balance that the amount of processing that you do is really critical in order to maximize the storage capacity of graphite. And we spend a lot of time working with our customers to maximize and optimize that process before you go to scale up. The last thing that's really important is particle size distribution. So we can't just use everything that comes out of the spheronizer because we get a range of different particle sizes. For most battery companies, they're looking at in an energy cell, they're looking for a particle size of about 15 to 17 micron. They're looking for a really tight, what we call D50. And that's why they want as much of that particle size at that 15 to 17 micron as possible, because they know from calculations they can maximize the energy in the cell. But you're saying, well, what happens to the big stuff and what happens to the small stuff? Well, the small stuff gets used. If you have a high power cell, you can use the small material, whereas the big stuff is probably going to be reprocessed where possible in order to try and maximize its use, or it will go to another application. Once you've got your spheronized particle, remember it's still only 89 to 95% total graphite content, and so it still has impurities present in there from the actual mineral ore body. And hopefully you've done your due diligence before you started this process, so you actually know what the residual impurities are. So what we would do at that point is then work on a purification process to actually remove and liberate the last of those impurities to bring up that impurity the processability. So there's plenty of ways you can do this. There's hydrometallurgy, and this generally takes a point around, as you can see here, there's a whole range of tests here that we can do. You can do things such as using sulfate and peroxides to deionize water to wash out those impurities. The other one that you'll see here on the bottom left-hand corner is HF leaching. This is generally only done in China because it's really hard to dispose of HF. And for any of you who understand HF, this is as toxic an acid that you can get. If you get this on yourself, you're in a lot of trouble. It's not something that you should play around with. So we've been working quite hard to actually look at developing new processes which are cleaner and greener and getting rid of that HF step there. There's also another step you can use, pyrometallurgy. Basically, you can heat this up to 2,800, 3,000 degrees Celsius and basically melt out the impurities. Graphite's great because it'll just regraphitize itself at that temperature, so you won't actually lose anything there, so it's quite useful. The last step is carbon coating. So now you've got a 99.99% graphite, and what you're now trying to do is to reduce the surface area further. So earlier I spoke to you about solid electrolyte interphases and that surface chemistry and those surface reactions. We want to remove those as much as possible. So what we're now trying to do is to reduce the surface area further, to get it as low as possible, and while maintaining the same particle size, so we can get the best electrochemical performance. And so what you can see here in these micrographs on the bottom right-hand corner is we're trying to get a very, very thin layer of amorphous carbon on that surface. It's transparent to lithium ions, it's electrically conductive, and this is and it will prevent the bulk reduction of the electrolyte on that surface. This is the secret sauce that most battery companies do. They'll normally ask you for the spheronized purified material, and then they'll normally put their own special coating on that material before they put it into battery anodes. And then lastly, you've got to then go away and build a battery. So you now then take that graphite, that carbon-coated, spheronized, purified material, you make an ink or a slurry, where you add some extra materials and a binder, and you coat that out onto copper foil. Copper is the only thing that's stable at the anode side. You can't use aluminium because lithium will alloy with aluminium. That's why they use it in aerospace. So you have to use copper for this process. Then you'll get it onto a very long winding. Most companies can produce this at hundreds of meters of a minute. They can wind up cells, thousands and thousands of cells a day. This is a fully automated process. But the graphite properties, all those properties I've shown you earlier, are critical to getting an excellent quality battery. And this is what it looks like when you finish. You can see here, this is a micrograph of the current collector and the graphite that's smudged into that electrode, depending on the size and thickness and the capacity that the company is looking for in its target energy density. So the natural battery graphite value chain has to be sustainable. This is another critical point here, and there's quite a lot of work that we're doing here around how do we actually deal with some of the energy intensity, some of the plastics, some of the electrolytes. You can see here that graphite makes up 22% of a battery. It's actually quite a substantial amount of material. Copper makes up 17%. So there's quite a lot of work to be done here to ensure that we have all the sustainable materials that we need to make this work. Recycling is a critical point, and this is definitely at end of life. At the moment, we don't have large amounts of volume of recycled material. There's just not enough to make this economically available at this time. Most companies are vertically integrated. So Tesla, for instance, does a lot of its own recycling from its manufacturing facility to recover its own materials, because cell manufacturing is only good to about 85% acceptance level. So the other 15% of cells have to be recycled and the materials recovered and put back into the manufacturing process. But depending on the process that you use, you may end up either going back to a concentrate, or you might go back to a spheronized material, depending on the processes that are used there. And recycling is a whole other story entirely. We have a battery recycler here in Melbourne, EnviroStream, who actually crushes and shreds batteries and turns it into what we call black mass. So that's all the materials higgledy-piggledy into a container, and then you have to then go away and float that material out and recover it. But at the moment, graphite recycling is done via a hydrometallurgical process. You can't do that pyrometallurgy. You'll just turn it into CO2, which is not the best way forward. So there are processes which are being developed in order to recover these materials, and I'd be happy to talk to you further about that. At CSIRO, we do some of this work as well. Lastly, just quickly, this is where the current breakup occurs. Spheronization and purification is pretty much 100% done in China. Carbon coating battery anodes, there's obviously quite a lot of work going on in other countries, and this is going to further diversify, particularly with cell manufacturing in Europe and also into the US as that quickly accelerates. So there's quite some opportunity here to see further diversification in this area. In terms of the value, why would you want to do this? Well, the further you process, the more money you're going to make. And I've only just given you some ranges of amounts of money here. Probably the guys at Benchmark will probably be able to give you much better accurate numbers around this. But depending on how far you're willing to go down the processing line, there's a lot of money to be made in this area. In Australia, there are quite a number of companies who have either ambitions or designs to do so. So Mineral Commodities, Renascor, Lithium Energy, just as a few examples, Ecograph, and also International Graphite. But there are other emergent companies who are also going there. And when we think about battery anodes, the type of company that would be taking that type of material on in Australia would be a company like Energy Renaissance. So just some quick final thoughts. Graphite will be the dominant lithium-ion battery anode material. You don't have to worry about that going away anytime soon. The amount of investment into this area is so substantial. I don't see this moving in any time soon, and it will be the basis of really high-energy battery chemistries. So demand will remain high. Technology is advancing slowly, so there are some technology challenges coming. As I mentioned earlier, silicon is one of them, but there are still significant technical challenges that exist there to making that actually work commercially. Next generation chemistry, such as lithium metal, the higher energy ones, are there, but again, there are technical and supply chain issues that have to be tackled. And of course, you have the emerging new chemistry, such as sodium-ion, which will capture some of the lithium-ion phosphate battery market. But again, there's still going to be a huge amount of demand for things such as other lithium-ion chemistries. There's definitely a need for graphite. As you've seen, there is quite a bit of processing that has to be done around this. And as I've shown you, artificial graphite is energy intensive and pretty polluting. So natural graphite, with its higher levels of ESG, has some great opportunities to capture some of this market. And some of the stuff that needs to be considered include, sustainable final stage purification processes, improved yields, and carbon-free mining. And social license is important too. The amount of new mines that have to be brought online, people have to be brought along on this journey. And there is a strong need for new mines. The current demand for energy storage is exploding, and needs to be far more material developed. So there has to be more mining done to be able to support this. So there's huge opportunities here for Australia and other places to move into this market. And with that, I'd like to thank you and now take any questions that you might have.
Are there any questions?
Thanks for the presentation. Just interested in your views around artificial graphite from a performance perspective versus natural graphite, and how you think that might evolve for natural in the future.
So artificial graphite is the dominant material in the marketplace at the moment. It's really well characterized and works extremely well. So most suppliers such as BTR, Showa and others are selling you an artificial material at the most in most instances. It's a very stable material, so it's well characterized and it doesn't have any of doesn't have some of the well-known degradation mechanisms that natural graphite has, which is one of the problems it has is a swelling issue. So with time, the particles will expand and contract, and you'll lose electrical contact in the material, and also you have some additional SEI challenges. So some of that can be dealt with through the processing mechanisms, can also be dealt with through the carbon coating, and also some electrolyte additives. So we're seeing more and more natural graphite come into the market, and we're seeing blended material being sold. So you can purchase mixtures of artificial natural graphite mixtures on the market now, but there will be far more 100% natural graphite electrode materials available in the near future.
Thanks.
I think we had one more.
It is in addition to with the artificial graphite, is that the main source for current lithium-ion battery mechanism?
Correct, it is.
And also you mentioned HF leaching process. So that is on the processing end. So
that's right.
That process is done in China.
Correct.
And what CSIRO is working on making that process, maybe a different process to make it safer.
Correct. So, I do understand that CSIRO Resources is also using a HF-based final step purification at their Vidalia plant in Louisiana. But we at CSIRO have actually developed a caustic processing method, which is actually able to regenerate that final step purification solution. So we can actually take out the impurities from that solution and reuse it again. So it makes it far more sustainable. And we can actually tune that to the impurity matrix. So if we do good characterization at the initial step of the graphite process, we can actually work out how we tune that caustic to actually remove that impurity matrix quite easily. And we've done that for 4 miners now here in Australia.
Could I just ask a question? Just, I followed graphite for a little while, and I often see presentations like this where demand is increasing and very strong. But when you look at the market, the price has been flat, and there's a lot of projects that are out there, at the PFS stage, but none are really getting off the ground. So just interested in your thoughts on that, and while the macro seems to look good, really activity is pretty low.
Yeah, I think there's a lot of price pressure, and I'm probably not the best person to ask this. It's probably the benchmark guys, but we see from talking to battery OEMs, price, they're heavily squeezed because they're squeezed by the automakers or the end users, and the battery materials makers are trying to maximize the value, and the OEMs are trying to the cell makers are trying to pass that pressure down the line. So they're trying to minimize the amount they pay for these materials. So this does lead to a chicken and the egg problem of, they're complaining that there's not enough supply, but they're not also paying top dollar. And this is because most of the cell chemistries you see today are now mass sold commodity products. So it's very hard to get that high price premium, I'd argue. So that does make a big issue, I will say that. But I think you're going to see, simply by sheer demand, that the pool's going to increase very strongly, particularly with now every country having some mandate towards net zero, renewable energy uptake. And to do that, you need more storage. This will this should hopefully correct some of those price problems that you described. When, I don't know though. Yep. The tipping point's been reached, so that's basically been COVID and supply chain crises and people trying to untangle themselves from China. People are now actively looking for alternative supply chains. That's why you're seeing governments, both in Australia, the US, Europe, coming out with critical minerals plans to try and diversify supply chains, trying to open up new markets such that everything doesn't run through China, because that's now considered to be a major impediment to being able to provide this localization of technology and manufacturing. So I do see these type of technologies all of a sudden taking off in the very, very near future, because most countries won't probably allow synthetic graphite manufacture, and most companies probably couldn't afford it with the current electricity prices. You'd need to have a pretty big solar field to make this work, or cheap hydroelectric power. So I think natural graphite will very quickly take off for the very reason that there's this diversification in supply chains opportunity that's happening.
Okay, thank you, Adam.
Thank you.